All right, so where we left off the other day was basically just getting you started introductorily, talking about the atmosphere. All right, going to take it a little farther today. We're going to borrow a few words from physical science class, physics class. I'm going to throw a couple formulas at you. Please don't worry. I'm not going to make you calculate anything using these formulas. I'm not going to make you remember these formulas. They are here because I'm pretty sure you can read formulas if you know what the variables are. And it really helps explain what's going on. So, formulas. We got two things we're interested in the atmosphere, and that's air pressure and air density, in addition to composition, of course. We'll talk briefly about air temperature as well. So air pressure and air density, and they're related, okay? So how are they related? Well, density, as you may recall, is mass over volume, right? D equals M over V, remember that? So how densely packed something is. I always like to use it. It seems to resonate with college students. Let's pick your favorite, you're not old enough to go to bars yet maybe, but your favorite establishment, all right? And on some nights it's super, super, super crowded, and some nights not so much. Well, let's assume that the volume of that bar doesn't change. In other words, they haven't put an addition on or opened up a patio or anything like that. It's just always the same size, right? That's your volume. Your mass is the amount of people in there, okay? So how densely packed is obvious at this point then. How many people are in there per that space? The more people per space, the more densely packed it is. You can use numbers to prove that, but again, I think we've all been in a situation like that. You've been somewhere twice. Once it was really full, once it wasn't full. You may not have said, by golly, it's densely packed in here, but, you thought something similar. So we're not talking about bars, we're talking about air. And I know if you look out the window, or heck, even look next to you, you've got air. You're not going to see the molecules. You can't see the molecules. And hence it's also kind of difficult to tell whether or not it's densely packed or not. And you may be wondering, well, what could we put in there? What could there be less of? All right, and we'll talk about that to some extent. This is where a weather class could go off in a completely other direction for some time. We're just introducing the idea here. So bear with me. If you're yearning for more information later, we can touch base. All right, so density is mass over volume. We want to talk about air pressure next. All right. Again, you may remember this formula, you may not. Force equals, pressure is force times acceleration. All right. That is a number of things. You can look at that as a giant linebacker running at you. You could look at that as being at the bottom of a pile of your friends. You're playing Twister, and everyone collapses. Okay. The acceleration varies in the conversation. If it's the football player, well, they're accelerating upon their own selves. If it's, just a collapsing pile of friends, that's acceleration due to gravity. Again, you don't really need to worry about it, but that's acceleration, okay? So the pressure you feel is the force and how much that force is accelerating against you. Well, what the hell is force? Force is mass times area. Whew, forgot that one for a second. Or no. F equals, I think that's just, should be a capital A. No, mass times acceleration. It's force. We have lately been learning about force in the Giappo household with our 65-pound poodle who still thinks she is 15 pounds and a tiny little thing, and she runs and jumps at you and everyone else and knocks them right on their butt because she bounces really fast and she weighs 65 pounds, and people don't expect a dog to do that to them. So that is mass times acceleration. That's force. Where is this all connected? How is this all connected? You see those M's in there? It's those there M's. Okay? So it's the same thing. We're looking at the amount of molecules in the atmosphere, and we're going to take away two things from this. We're going to take away, first of all, that the air is most dense near the surface of the Earth. So as you go up through the atmosphere, you're going to encounter less and less air molecules. Remember, that's what makes it dense, right? So the air molecules are most densely packed near the surface of the Earth. Who can tell me why? It's actually a much easier reason than you might think. Well, why do we have an atmosphere? Gravity. What do we all know about gravity? Yeah. The closer you are to it, the stronger it is. More or less. So the closer the molecules are to the Earth, they're going to be stronger. It kind of self-feeds, okay? So all these air molecules, they cluster up closest to the Earth because the force is the strongest there. Some of them did manage to escape. The air thins out. You've known that probably forever. You hear about, Mile High City in Colorado, okay, Denver. The air's really thin up there. Someone goes up a mountain. You hear about Sherpas. You hear all kinds of things about how the air's thinner, airplanes, and so on and so forth, right? So we've known this forever. We're just kind of reminding you that it's actually a thing, it's pertinent, it's relative. And now we're telling you why. Air pressure is the entire column of air. Believe it or not, they measure it in like 1 little inch squares. Okay. You remember that thing? I really don't know its name, but everyone more or less knows what it is. It's usually a bunch of pins. When I was a kid, it was metal pins in a little box. Nowadays, you see cheap plastic ones, and you used to see them at like Spencer's or whatever, and everyone would kind of like walk by and make some weird little hand sign, usually a middle finger pressed into the pins, and you would see. Anyone know what I'm talking about? I'm gonna find one on the internet and show you guys one of these days. It's just a loose little nails. Pins might be the wrong word, but they float freely in it, and it's pressure. You push on it, you can make some cool little wavy design. See a couple scrunched up faces out there. So we'll Google one later. Imagine walking through that. All right, as you walk through that, those pins go up and down, up and down. Each one of those little pins represents a column of air. Okay, in this analogy. Basically, air pressure is the mass of the air above you pushing down on you. If you're at the Earth's surface, is air pressure going to be higher or lower? Do you have more or less air pushing on you? If you're down on the Earth's surface and you have a whole column of air above you, is it going to be more air than if you're at the top of a mountain, or less air? More. Good. Okay. Because you've got that much more air above you. It's that simple. If you're at the top of a mountain, why is the air pressure lower up there? Because you have that much less air pushing down on you. It's literally a function of those air molecules responding to gravity. All right. So we could say the weight of a column of air. Finally, we could use the word weight maybe. All right. Correctly, semi-correctly. Even though in the equation it's still talking about mass. But they wouldn't be pushing down on you if it weren't for gravity. So, both of those decrease with elevation. All right? Both air density and air pressure decrease with elevation because of the reasons we just discussed. The air molecules tend to clump up near the surface of the Earth. And as you go upwards through the atmosphere, there are less air molecules. You would expect to find your highest pressures at the surface, lowest pressures up above, highest density at the surface, lower density up above. Gabish, we good? Okay. And like I said, the equation is just there to confuse you. Why won't we change slides here? There we go. So this is just another way to show you this lovely little graphic here. It shows you that, because this is just a wonderful example that everybody knows, but you have heard about Mount Everest. Before you reach the top of Mount Everest, you're above 50% of the atmosphere. You're above 50% of the molecules that make up the atmosphere. That's pretty dang close, okay, is kind of the point here. Whether or not you could achieve the top of Mount Everest is irrelevant at this point. But the fact is it's a thin layer. That's what we're trying to get across here. Up where an airplane flies, okay, you see that understandably it's even way less. Are there still air molecules out there? Absolutely. Okay, there are even molecules flitting around in space, and we'll talk about that a little later.
How tall is Mount Everest?
According to this here thing, it looks about 8 kilometers. In feet, I couldn't do that in my head. But pretty dang tall. But in respect to an atmosphere, you would like to think we got more than that. Well, let's actually, because this proves a great point. Well, let's ask our friend Siri here. How many miles is 8 kilometers? How many miles is 8 kilometers? 4.97 miles, so 5 miles up-ish. That's just ballparking. All right. So why did I waste our time to do that? Think of somewhere that's 5 miles from here. The mall, maybe? Might be a little closer than that. Going out to Bonomo's for ice cream. Definitely 5 miles. So you go that way in what, like 10 minutes in your car, 15 minutes? You got to get across traffic, everything. You go that far straight up, you're practically out of air. All right, that's the idea here. It's thin. Okay, relatively speaking, all things considered, for what you guys are used to jettisoning about the surface of this earth for, it's really, really thin. Talked about this. We did not give you a value, though. 14.7 pounds per square inch. All right. That is atmospheric pressure. You don't ever hear it that way, though. Again, please don't just scribble all this stuff down. You got access to this, bless you. If you didn't print it out, you should. But, yeah, you just print these out. You never hear about 14.7 pounds. You hear, if you pay attention to the weather and stuff, you see 29.92. That's what the weather person's going to tell you. All right? Or 29 point whatever. It does change. It doesn't go much. I've seen 30. I don't know that I've ever seen 28. Okay? But it does change. What is capital H, lowercase g there? Yeah, mercury. This is a hygrometer, and it's used to measure atmospheric pressure. Why we ended up with mercury, I don't know. It's not the best substance to work with, obviously. But I keep saying this, one of these days I'm just going to take a weekend and study hygrometers, how they came to be. What it boils down to is this: picture a U-shaped tube, all right? And you've got one end more or less capped off so air can't bother it. And then the other end is capturing air, and it's filled up with mercury too, by the way. And it pushes the mercury around the other side of the U up to 29.92. All right. You put more air molecules in the air, that puts more air pressure in the tube, more weight in the tube. It pushes that mercury up higher. You have less air molecules out there. It's pushing down on the mercury that much less. So standard atmospheric pressure, as they say, 29.92 inches of mercury. That is, again, supposedly at sea level. Let's do some handy-dandy quick use here. And on. How far do I have to scroll here? 29.76 right now. 29.76. So we're lower or higher than standard atmospheric pressure?
What did you say it was?
29.76.
Low.
Yeah, we're on the low side. All right. And this just goes to show you why weather takes advanced calculus and whatnot. Because you look outside and you think, oh, it's kind of crummy and kind of rainy-ish out there. There's humidity out there, so you would think the air would be a little heavier today, right? So it's unfortunately not quite that simple, and we're not going to get into it. Even in Earth science, I wish we could, but we only have like 2 weeks for weather. So weather's crazy. It really is. There's a lot to it. We've come a long way in our understanding of it, how it works. But it's fluid dynamics. Like I said, it's Calc 4 kind of stuff. Always made me sad when students would come and say, I want to transfer to Oswego to take meteorology. And they're like in math 050. I don't think we have 050, but we still have a math that starts in 0 something, I think. And I'm like, okay, you can do it, but you've got 8 math classes to go through. And that smile just melts off their face. Again, it can be done, but they do a lot of heavy coursework, physics and calc. So, and if you dig that kind of stuff, please, we need more people interpreting those computer models. All right. We told you nice and simple, flat out, as you go upwards through the atmosphere, what happens to both atmospheric pressure and atmospheric density? It increases or decreases? Decreases. That is not so with temperature. Temperature is that red line going through the middle of this diagram. All right? And I'm not going to ask you to memorize every little thing here. But there's a couple that we do want to talk about. First of all, you probably don't remember, but last time we talked, at one point I briefly mentioned that we live in the troposphere, right? The troposphere is the bottom white there. You see Mount Everest again for reference. Gotta love that Mount Everest reference. And the small, tiny words down there do say troposphere. Above that is the stratosphere. Most folks have heard of the stratosphere. We told you the stratosphere is where the ozone lives, and that's also it's pretty high up and kind of cool. We just like the stratosphere. Bless. Above that, we got the mesosphere and then the thermosphere, and you will sometimes also hear about exosphere. Don't worry about the pauses. The pauses are non-existent lines in between them. They blend, all right? But folks in charge, of course, felt the need for more vocabulary. So between the troposphere and the stratosphere, we have the tropopause. Between the stratosphere and the mesosphere, we have the stratopause, and so on and so forth. And you notice that they at least kindly made it a dashed line to tell you that it's not like a real thing. But you want to remember your ospheres. So in the troposphere, what does that red line do? I don't know if you guys can actually see the scale from where you are. It goes to the left. Is that an increase or decrease in temperature? Who could read that scale from where they're sitting? It's a decrease. And you probably, again, knew this. All right? As you go upwards through our atmosphere, it gets cold. When I was a kid, we used to call them bomber jackets. Bomber jackets were really hip and really cool. All right, big leather coats with the fuzzy Sherpa lining on them, and those are what the guys wore in World War II flying the planes. All right, we just thought they looked cool. Well, you know why they had to wear those things? It was really freaking cold up there. So they didn't wear them because they thought they looked cool. They wore them because they were so cold. All right, those big hats too. All right, that's why they wore those things flying around up there. It's cold up there. All right, how much the temperature drops again, not a value you need to worry about. But more importantly, again, we want to follow that red line. Okay? So we see that the temperature drops as we go upwards. Then when you hit the stratosphere, it kind of levels out for a little while. Then it actually starts to increase. We're calling it an increase because it goes back to the right, almost to where it started, right? That line of arrows coming down the side is where it starts-ish. So you see that bend there, right at the stratopause, is close to average surface temperature. Then it decreases again, and then as we enter the thermosphere, you see the indication that it keeps going up, but the graph ends. And I want to tell you that it keeps going up, and it keeps going up, and it keeps going up. And it keeps going up. There is, I'm sure, a limit somewhere, but it goes much higher than average surface temperature. I gotta check my slides real quick, and I think we're coming back to this one. Yeah, so I just have a little side note here, and then we'll move on. So, the reason that the temperature keeps going up is actually fairly simple. Does anyone know, sometimes people do, sometimes they don't, what temperature is actually a measurement of? And not how hot or cold something is. I know that. We all know that. What is temperature a measurement of? Okay. Temperature is a measure of molecular speed. Molecules vibrate. Okay. So the faster something is vibrating, the higher its temperature is. Moving. Okay, we'll just say moving instead of vibrating. The slower a molecule is moving, the cooler its temperature is said to be. In this context, absolute zero makes complete and utter sense. When I was in your positions, I don't know if I was doodling or whatever, but or they just didn't bother with that little lead up. Because for the longest time, I thought absolute zero just meant it was so damn cold that even the molecules couldn't move. Okay? That's what I thought it meant. Well, no. It is cold because the molecules aren't moving. And I know that's kind of a weird way to think about it.
So how do you figure out negative then if they stop moving at zero?
Who stops moving? Oh, absolute zero. Well, that's you ever heard of Kelvin?
Yeah.
Yeah, it's Kelvin stuff. Mine's 273 Kelvin, I think, is absolute zero. Yeah. So it's way beyond Fahrenheit and Celsius. Great question, actually. Yeah, it's a good one. Yeah, I'm pretty sure mine's 273 Kelvin is absolute zero. So, yeah, it's just the molecules stop moving and it moves upwards from there. There is a Kelvin to Fahrenheit to Celsius comparison table somewhere out there in the world. It's kind of neat the way it lines up. Kelvin came afterwards, obviously. So he lined up his stuff. It's pretty neat. I forget. 212 is either Fahrenheit or Celsius. I'm not even going to guess because I don't remember. But so at any rate, so no molecular speed. How does this temperature keep going up? Well, as you go up further and further in the atmosphere, you are farther and farther away from the Earth's gravity, right? Therefore, as we already talked about, you've got less molecules banging around up there, and you also have less, what slows things down? Kind of related to gravity, but not exactly. Friction, all right? You got like no friction up there because there's hardly anything to rub against. So these molecules are flying almost as fast as they possibly can. So by proxy, their temperature is very, very high. So why do they always say the cold, hard void of space then, right? Well, it's that whole void part. All right, why do astronauts' heads blow up when they lose their helmets in all the movies? There's no air pressure. Remember, we've been talking about pressure. There are molecules there, as I said earlier. I stand by that, but they're just tennis balls on a football field kind of thing. If you did get hit by one of them, maybe golf balls on a football field, I don't know. If you did get hit by one of them, it would be very, very, very hot. It would burn you very, very much because it's traveling really, really fast. But we tend to run out of air before we get enough to actually sustain ourselves on. So that's a cool little thing about temperature and space and molecular speed, and just to remind you of a few things in there. And I usually do one other little experiment here, and for the life of me, I can't remember how I segue into it. So I'm just going to have you do it. I want you guys to touch your notebook with you pick a finger, any finger, and touch your notebook with it. All right? And then, or your laptop. Okay. Touch your mouse pad there. All right. Now I want you to reach down and find a piece of metal on your desk with the same finger. No, not on your notebook. It might work, but touch your desk instead.
Something in here, right?
Okay. Which one is warmer?
Notebook.
Notebook. Notebook, 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 notebook. All right. Is there any reason on God's green earth why your notebook would be warmer than your desk? No, absolutely not, right? I mean, you can't think of anything. I can't think of any reason. They're not. They're both the exact same temperature. Temperature is a sensation. It goes back to our conversation about space, and that's my segue. All right, you have to perceive temperature, okay? What's actually happening when you touch the metal on your desk? Metal's a great what? Conductor. All right? That metal isn't colder than your book. It's stealing your heat better than your book is. If that makes any sense at all. So, it's your finger that's cold, not the metal, not your book. You can feel your forehead, your notebook, and your thing. They're all, well, your body temperature can vary, but don't feel your forehead. But anything that's not alive, all right? So it feels colder because it's better at stealing your energy. It just made your finger colder than that piece of paper does. Paper's not a great conductor. So temperature is a sensation. Temperature has to be felt. And the only way you could feel temperature is when those molecules are hitting you. All right? Bringing it all back home with some weird little stuff in the middle there. Questions before I go any further? Okay. So I told you don't have to remember the temperature by the time you get to the stratosphere, but we do have a vocabulary word, and it's called lapse rate. And a lapse rate is the average decrease in temperature through the troposphere. And it's about 3.5 degrees Fahrenheit for every 1,000 feet you go up. So lapse rate applies to decrease in air temperature in the troposphere as you go upwards. And it's 3.6 degrees, or as I said, about 3.5 for every 1,000 foot you go up. So it doesn't sound like those old pilots should be that cold, right? But, you got leaky planes. I don't know. No, they couldn't have leaked that much, or they wouldn't have been able to fly them very well. But you add it up. You keep going. It adds up. All right, lapse rate. We got about 7 miles of air. Yes, there's molecules in all of those layers, but what you consider the atmosphere, you got 7 miles of air. And even looking at that, if you were to go up 7 miles, you wouldn't be able to breathe anyhow. Right? You go a couple miles, and things start to thin out. Has anyone ever been out west? Difference in air? Depends. Depends. You guys are young and in shape. You might not notice it too much. Maybe if you go run a race there or something. But it is, your ears notice, heck, even a couple 100 feet, right? When you're driving in your car, your ears pop. That's the idea. If I were to ask you where space started, that would be the exosphere there. That's really surprising to a lot of people. That may not be a trip to McDonald's, but many of you have driven farther than that. Potentially many times. And again, just aim your car up and try and do the same thing. You'd run into trouble really, really quick. Solid. And just one more slide to round it out. We mentioned the other two, first two gases very early on. Somebody asked, what's that other 1%? You notice this goes over 100. There's some rounding going on in there. I mentioned the carbon dioxide concentration the other day. I forget how it came up. And it's so tiny. But it is what Mother Nature set it at. It's the important part. And when they talk about it going up or down, and it has gone down too. That's what throws us into ice ages. We've got air trapped in ice that we've measured. We know CO2 levels for many, 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 many years of Earth's history. So these folks know what they're talking about, but people see that number and they're like, oh, that's such a tiny number. It's where it's set. So, all right. I'm going to stop the recording here. It's a nice little length for the folks at home, and then we're going to start it back up with a new section as well.